Let's start by recalling what a function is. So a function is a rule which assigns to every element x of a set D exactly one element of a set E. And it can be viewed as a machine-like object which acts on a variable to transform it. Here's an example. The function f of x equals 2x plus 1. It changes the variable x, or the number x, by multiplying it by 2 and adding 1. And we can get a lot of information about the behavior of a function by either using algebra or using calculus, using derivatives if they exist. And we can also gain a lot of information by sketching the graph of the function and using our basic graphing techniques from pre-calculus to graph it, or perhaps the more sophisticated ones from Calc 1. The graph of every function passes something called the vertical line test. When we graph the equation y equals f of x, every vertical line cuts the graph at most once. That's because to every x, there's associated exactly one value of y on the graph. And in fact, if we have an equation and the graph passes this vertical line test, then theoretically we can solve for y in terms of x, and it is the graph of a function. Now we're going to look at some very special functions, or functions with a special property called one-to-oneness. And this property amounts algebraically to saying that whenever I have two different x values, x1 and x2, then f of x1 and f of x2 are also different. The function f of x equals x is 1 to 1. How do I know this? Well, I can verify this simply algebraically. If I have two different values, x1 and x2, then f of x1 is not equal to f of x2 by definition, because f of x1 is x1 and f of x2 is x2. On the other hand, g of x equals x squared, this is a function which is not 1 to 1. And how can I demonstrate this? Well, I can actually come up with two different values, x1 and x2, for which g of x1 is equal to g of x2, and it violates that condition in the box. And those two values, as you can see, are minus 1 and 1. Note that to prove that a function is not 1 to 1, it's enough to find just one pair of numbers, x1 and x2, which violate that condition in the box. But on the other hand, if I want to prove that something is 1 to 1, I have to somehow demonstrate that no matter what two numbers I take, x1 and x2, which are different, f of x1 cannot be equal to f of x2. So it's a much more difficult process. One thing that can help is the graph of the function. So a one-to-one function has this special algebraic property, and geometrically it has an analogous geometric property. So saying that a function is 1 to 1 is equivalent to the geometric condition that no y value appears in the graph twice, or no horizontal line cuts the graph of the equation y equals f of x more than once. And here I've sketched the graph of the two functions we've just looked at. Y equals x is on the left, and y equals x squared is on the right. And I've also drawn some horizontal lines. So you can see that the lines y equals 2, y equals 10, and y equals 20, they all cut the graph of y equals x squared on the right twice. So this violates our horizontal line condition, and therefore the function x squared, f of x equals x squared, is not a one-to-one function. On the other hand, we see on the left that any horizontal line we draw cuts the graph of y equals x only once. So we have no horizontal line which cuts the graph more than once, and we can conclude that the function is 1 to 1. So we can make a test for checking whether a function is 1 to 1. If we can sketch the graph, we say that that graph passes the horizontal line test if every horizontal line cuts the graph at most once. So a function is one-to-one if and only if the graph passes this horizontal line test. And here we've graphed two functions, a cubic on the left and y equals the square root of 4x plus 1 on the right. And we're going to use this horizontal line test to check if these functions are one-to-one. To check if this cubic passes the horizontal line test, we just have to slide a horizontal line along the graph. And we see that below this turning point, the graph passes the horizontal line test because the lines cut the graph only once. However, in this region between the two turning points, every horizontal line cuts the graph 3 times, so therefore our graph does not pass the horizontal line test, and this is not a one-to-one function. For y equals the square root of 4x plus 1, if we slide a horizontal line along the graph, it never cuts the graph more than once, so therefore this function passes the horizontal line test. Now you see below the x-axis, each horizontal line cuts the graph 0 times, but this isn't a problem. This doesn't violate the condition that a horizontal line must cut the graph at most once. Now here's a very special example. We all know that the function f of x equals cosine of x is a wave-like function, and any horizontal line y equals a, for a between -1 and 1, is going to cut the graph infinitely many times. So we can easily say that this is not a one-to-one function. And here I've drawn a portion of a wave, and we see several horizontal lines cut this graph twice. Therefore, we're absolutely sure at this point that the cosine function is not one-to-one. However, I can restrict the domain of this function to create a new piecewise defined function called the restricted cosine function, which is one-to-one. And if I restrict the domain to an interval between 0 and pi, then if I let the piecewise defined function g of x equal cosine of x on that interval, and it's undefined otherwise, so the domain is between 0 and pi, we actually have a one-to-one function. So I've drawn the graph here, which is just a piece of the graph of the cosine function, and you can see that every horizontal line between -1 and 1 cuts the graph exactly once. Horizontal lines outside of that range don't cut the graph at all, but that does not violate the condition for a one-to-one function. So therefore this restricted cosine function is one-to-one.